Hi you guys, this is Valdivia. So I'm going to go over chapter 4 practice worksheet that is found on your Canvas. This is not credit based, it's just for your own benefit so that you could practice along with me. So if you're on Canvas, you go to modules, and on week 4 module, for chapter 4 module, week 4, let's go here. It is under in-class worksheet. So module 4, week 4, in-class worksheet. Like I said, it's for your own benefit, not any credit, but I do highly suggest you print it out and try these problems. You could try them on your own and double check the video, see if you got them correct, or you could follow along with the video and do them with me. Right, so first question. Find the frequency and energy for a photon of light with a wavelength of 370 nanometers. So we're looking for frequency, energy, and we're given our wavelength. Okay, symbol frequency, energy, and wavelength. We have two equations that we're going to be using. We're going to use the equation of speed of light is equal to wavelength times frequency, and we're going to use energy is equal to Planck's constant times frequency. Okay. Starting with the first one, because we have wavelength, it was given to us and we don't have anything else, we're going to use this one first. So speed of light is equal to wavelength times frequency. I'm going to solve for frequency, so I need to isolate that variable. So I'm going to go ahead and divide both sides by my wavelength. So now I am at frequency is equal to the speed of light divided by wavelength. I'm going to go ahead and continue up here. Frequency is equal to the speed of light, which is 3.0 times 10 to the 8 meters per second. And let's verify that that is the actual number, and units, because sometimes we get it messed up, right? We don't get to mess up, actually, because you get it wrong, you get it wrong. All right, it's this, meters per second, so we're going to verify that. And it was correct. Now we have wavelength, which is 370 nanometers. All right, now you'll notice right away that we have meters on top and nanometers at the bottom. We won't be able to properly do that mathematics. We have to convert the units. In order to convert the units, I'm going to do the bottom one because it's just the smaller and easier number to work with for me. Okay, I'm going to take 370 nanometers, and I'm going to use the conversion factor of 1 meter, and there is 1 times 10 to the 9 nanometers. Okay, so what does this conversion mean here? Because that's probably the hardest part for most of us. It's saying that in 1 meter, I have this many nanometers. And that makes perfect sense because a nanometer is extremely small and you need this many in order to fill 1 meter up. Okay, so that is this equivalency factor right there. Right, I do the math, and I'm going to get 3.7 times 10 to the negative 7 meters. And if you guys want to verify that, we go to 370 divided by 1 times 10 to the 9, and we have 3.7 times 10 to the negative 7 meters. Okay, so I could rewrite this now. I could do it here also, or I could rewrite it, which I am, to the 8th over 3.7 times 10 to the negative 7, and this is all in meters per second now. So therefore, my frequency, I'm going to solve this by putting on my fancy calculator, 3 to the 8th divided by my previous answer gives me 8.108 times to the 14th. So 8.108, whatever, all these numbers that we don't really want in our final answer, by the way. This is meters per second. We're going to rewrite our final answers in the correct number of significant figures down here. Currently, we are still busting out some work. Okay. Now that frequency is done, we're going to solve for energy. energy is equal to Planck's constant times wavelength. Energy is equal to 6.63 times 10 to the negative 34 joules times second. Whew, that's a big number. Times the answer that we found right over here, which was 8.1081 blah dot dot. I'm just going to use the answer directly from my calculator. I'm not going to delete that. Times 10 to the 14th meters per second. Okay, before we continue, I'm going to look at the similar units and see if there's anything I can cancel out. And so far, oh, by the way, did you guys catch my little mistake here? Because I just caught it. My mistake was I forgot to put my meters down here on this little section. And we all know that anything divided by itself cancels out. So that's a 1. So therefore, this is not a meters per second. It is just a per second. So it's a per second. Now you could also rewrite per second like this, if it helps. Okay, whichever one, they mean the same thing. Okay, so now I'm going to take this number and multiply by 6.63 to the negative 34. Negative 34. And I get, I should just leave the calculator on this side. Makes it a lot easier. 5.3756 times 10 to the negative 19. And here, let's look at our units. Seconds and seconds cancel out, and I'm left with joules. And that's exactly what I want. So now I can express my final answers correctly. Frequency is going to equal to, well, let's see how many significant figures we have to post. My original answer has 3 digits. Does this 0 count? Well, it's at the end, or it's following a whole number. All right, that's good. But it also needs to have a decimal in there. There is no decimal, so the 0 doesn't count. Therefore, I need to report my answer in 2 significant digits. So I need to report it to the 1 spot there. There's a 0 next to that 1, so I don't round it up. So frequency is 8.1 times 10 to the 14th per seconds. And energy is going to equal to, same thing, 2 significant figures. It's here that 7 is going to round that 3 up. So 5.4 times 10 to the negative 19 joules. This is my final answer. I'm going to box it up. And just because I like to do this, when you get to your math class or any other class that you have to turn in some work and show your final answer, highlight your final answer. It really, really helps in finding yourself. So box it up, highlight it, that great. All right, so we just solved that problem, okay? We did math. We used these 2 equations to solve for the frequency and to solve for the energy of it. Let's see. Okay, I think number 2 is quite similar. You guys should be able to do it. I'll guide you a little bit. It says a photon of light has an energy of this. So energy is given to you as 1.83 times 10 to the negative 18 joules. What is the wavelength? So you're looking for wavelength. You don't know what that is of this light. And then it's asking you, what does it fall into? Is it infrared, visible, or UV on that spectrum? So what you want to do is actually just Google a spectrum, a light spectrum, or open up your textbook to a light spectrum and look at the wavelengths. Where does it fall into? Make sure that you're comparing the correct unit. Whether if your book gives it to you in nanometers, make sure that you have this in nanometers. If it gives it to you in meters, make sure you have it in meters. All right, let's move on to another one. We're going to move on to problem number 3. Okay. So on problem number 3, it says, how did the Bohr model describe electrons within atom? How did the model explain the line spectra? All right, so going to our notes, when we start talking about the Bohr model, this is probably on the second part of our notes. All right, the Bohr model. Here it is. So the Bohr model has energy levels, okay? These are quantized amounts of energy levels, and it wants you to use that model to describe the electrons within the atom. Where are the electrons located based on the Bohr model? And how did we use it to explain the line spectra? Okay, so on, let's go to your book on chapter 4. Now remember, your book is also available to you on Achieve. You have your electronic copy of it. All right. So the Bohr model and wavelengths. Okay, you're gonna find it on page 91. So you're gonna refer to page 91 for this one in explaining the line spectra and how that works. All right. When you are talking about this one, some key words, because if you're going, okay, I'm not quite sure what I'm going to look for, is I want to see something about electrons, excited state, and electrons on the ground state. I think we briefly covered that in one of our notes. Okay, right here. Release energy, and it releases energy in the form of light, which is photons. And this light that we see, that's our visible light. Just like we said at the beginning of the chapter, we focus on visible light. So it's going to release light, and this is visible light. And every wavelength has a different color. So every wavelength has a different color associated with it. Okay, so you could use some of this, use some of the information on page 91 to describe the Bohr model, the ground state, and the excited state. Okay, basically our notes kind of gives it off, right? The notes that we just put there. Okay, quantum mechanics and electron orbitals. What is the Heisenberg uncertainty principle, and how does this principle affect our description of electrons? So we want to look for the Heisenberg uncertainty principle. Dun, dun, dun. And let's find it. All right, so give me a sec. All right, you guys, sorry, I had to pause it to look into your book and like, okay, what page? So it's actually page 93, but we covered it in our notes and we didn't use the word Heisenberg, and it's been a while since I've used that word and it took me off my guard, but it's just the uncertainty principle. That's all it's talking about, the uncertainty principle. So in the notes that we took, we start talking about the uncertainty principle right before we get to electron configurations. So it is impossible to know both the location and velocity of an electron at the same time. That is the uncertainty principle. How does this principle affect our description of electrons? Basically, electrons are in constant motion. That's what it is. They're in constant motion, and they reside inside of clouds, right? So these clouds are what we call our orbitals, those shape-like structures that we went through in our notes. Those energy levels, they float around anywhere they want inside an orbital. So again, uncertainty principle, it is, you can't know both the location and the velocity where it's traveling, those kind of things at the same time. Okay, you either have to know one or the other. By the time you know the velocity, you've lost the location. By the time you know the location, you've lost the velocity, kind of it. So, yeah, if you want to read more on that one, it is on page 93. All right, next one. The Bohr model described electrons in orbit. Quantum mechanics describes them in orbitals. What is the difference between these two terms? Remember, in orbit is something that is orbiting like the nucleus. So here's our nucleus, and here is an orbit. So the orbit goes around an object. In this case, it's going around this nucleus. So this is an orbit. An orbital is actually a section, okay? So my nucleus was there. We actually have a section in which the electrons could be traveling inside of. That's the big difference between them. The orbitals do not orbit the nucleus. They have their shapes already. And they're given spots and positions, and the electrons are not orbiting the nucleus, wrapping around it like a solar system. It doesn't do that, right? It's basically like how can I say it? You take an electron and you put it inside a bag full of air and you shake up the bag, you don't know where the electron's going to be at, right? So you don't know where the electron's going to be traveling inside an orbital versus something that orbits. All right, you guys, how many electrons can occupy each orbital? Hopefully you guys remember that, but if not, here we go. Each orbital can occupy 2 electrons. 2 electrons per orbital. All right. Complete this table showing the sublevels of each energy level and the number of electrons each one can hold. All right, you guys. So we actually did that one in our notes. So feel free to take this directly from our notes on here and complete it as you go through. So in this case, though, it's a little bit opposite. Here you're showing you have an S with 2 electrons, and then a P with a maximum, in this case, of 6 electrons in it, right? So it's just slightly different from what we did. Okay, now we're going to go into electron configurations, right? So I'll do, this is actually like the more important stuff here that we can spend some time with and figure them out. All right, so number 8 says, complete the sketch below to show the filing sequence for fluorine, then write the electron configuration for this atom. Okay. So here's our energy. Energy goes up. We have to look for fluorine. Okay, so fluorine is the one it wants us to do. Here, I'm going to go to your periodic table, and I have one here as well. Here is fluorine. It has 9 electrons on it. So let's move this here. So fluorine has 9 electrons, right? Because it's fluorine 9. It doesn't say it's an ion. And it is in the P sublevel. So it's in sublevel P. Okay. All right. So out of 9, we're going to start filling this up. So we start with the lowest energy level, put 1 in. And now we're going to have 2. Keep going. 1, 2. That's 4, 5, 6, 7, 8, and 9. Right? So this is where we end it. If we wanted to answer more questions, remember this electron here is the bonding electron, right? It has 1 valence electron that is available for bonding. Right? This one is for silicon. I believe you guys can try this one here on your own. Okay. Write the electron configurations for each of the following atoms. So now we're just going to write electron configurations. I'm going to do, which one should I do? Uh, let's do neon. Okay, so we're gonna do neon. Neon is located right here. Okay, so neon has 10 electrons. 10 electrons. So we're gonna have one S2, two S2, 2p6, and that gives me a total of 10 electrons. Now, I didn't do the arrow notation. I just did the electron configuration for it. And it didn't ask me for the arrow. I'm not going to give it any more extra than what I have to give, right? If you do want to do the arrow, it's one, hold on, 1, 2, 3. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then that would be your arrow notation that goes with them. Okay, we'll do one more. Let's do phosphorus. Phosphorus is right here. It has 15. Okay, so it's going to be a 1s2, 2s2, 2p6. Okay, and I noticed that I'm done here on the 2p6, so now I'm back to energy level 3 right here. So this is energy level 3, so this is 3s2. 3s2. And I'm now at 3p, and it's 1, 2, 3. Okay, and I'm going to count my electrons to confirm that I actually did that correctly. 2, 2, and 6 is 10, 10, 11, 12, 13, 14, 15 electrons. It was done correctly. So this one's for phosphorus. I'll let you try the other ones on your own. Write the electron configuration for the following using the noble gas shorthand notation. I'm going to do cadmium. Okay, I'll do cadmium, CD. So CD cadmium, let's look for it. It's right here. It's number 48. This is the nice one. So we're going to start, and it's going to be noble gas configuration. The last noble gas that it passed up was krypton. So I'm just going to go forward and then up one, and it's going to pass up krypton. So I'm going to put a KR, and I'm going to put krypton in parentheses. Excuse my dog's breathing. She's really old. So I'm going to put krypton in parentheses, and now I'm going to go ahead and write everything else that comes with it. So I'm going to be at 5s2. So 5s2. And then I'm going to go ahead and move to this row here. Now this is not a 5D, okay? Remember when I said this pushes up a level? So this D block right here starts in level 3. So use that 3 as your guide. It starts in level 3. So this is 3. This must mean... Hold on. Okay, so she's just being dramatic. She's completely fine. Is that right, Snow? Okay, so let's retry this. We have krypton, and it's a 5s2 right here. And this D block is going to be 3, 4, 4D. And we have to figure out how many to get to cadmium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4D, 10 to get to cadmium. And there is also a 5P, but it's going to be empty. There's nothing in my 5P. Now, we don't usually write it down that it's empty. However, that empty orbitals play a role in like exceptions and rules for these elements bonding with more than what's necessary, because they have all these spare orbitals, right? So those are spare orbitals in which you could add electrons in. Okay, so here is our cadmium. Okay, feel free to do the other one. Okay. Indicate the number of electrons in each ion, then write the electron configuration for each using the noble gas shorthand. Okay, so it wants the noble gas, right? So let's go ahead and do, let's do fluorine, okay, with the -1 charge. So here's fluorine. It normally has 9. So that's going to be 1s2, 2s2, 2p6. Okay, and the reason I gave it a 6 to make it a 10 is because it has a -1 charge. So with that extra 1, this is now going to be a 10 electron ion. Okay, and it has this notation. It's asking me though to do the noble gas notation. So what that means is I'm going to get rid of this 1s2. I'm going to actually write neon in its, actually not even neon, helium, because helium is the first noble gas on our periodic table. I'm going to write helium, and then I'm going to write 2s2, 2p6. So this ion is isoelectronic with neon. Okay, so it's isoelectronic with neon. It didn't ask that, but it's always a good habit to put down the little bits of information that you know. All right. Here's this next one. It says, on the table below the electron configuration of the outermost shells, label the electron configuration of the outermost shells. The first few are done for you. Note the larger atoms, some exceptions to the filing order occur. Don't worry about these. The key idea here is to learn the main pattern. All right, so basically we're just writing down the patterns. I told you guys that this was the S block, and I would actually take this opportunity to color coordinate a periodic table if you have it with the different blocks, right? So here is my S block. And my S block will also include this one here, that helium atom. Here is my P. Okay. So that's P. This is S. Um, D. And this bottom one is going to be F. All right, so if we write our electron configurations for these, it says it just wants the main pattern, right? What is the main pattern? Started off with the 1s, and we said that these are 2s's, so this is 2s1, this is going to be 2s2, okay? And guess what? This is going to be 3s1, right? What do you think that one's going to be? So we have 1, 2, 3, 4, 5, 6, 7. This one's 7. This one's going to be 7s2. Okay, you can go ahead and fill in all the other ones. We're going to label our P block. Okay, so our P block starts on the second row. So therefore this is 2P. And this is going to be 2P1, 2P2, 2P3, 2P4, 2P5, and 2P6. Okay? And you're going to fill all of them until you get to the bottom and figure out what that one might be. I don't want to get you guys confused, so I'll do one of these, 2, 3, 4, and this is going to be 5P1. Okay, because I don't want this part to confuse you. So the numbers are in order there. Now we're going to go to the D block. The D block starts with level 3. So this is 3D1. This will be 4D1, 5D1, 6D1, and all the way until you get to like 6D10. Going on to the F block. I hope you guys noticed the pattern. S starts with 1, P starts on the second energy level, D starts on the third energy level, so F is going to start in the fourth energy level. So this is going to be 4F1, 4F2, until you get all the way down to 4F14. Okay. All right. Now that you have that, a couple things more that I wanted to add is our orbitals. So we say we could have 2 electrons per orbital. So here is orbital 1, orbital 2, orbital 3. Okay? So that's how you end up with 3 orbitals. Here you go, orbital 1, orbital 2, orbital 3, orbital 4, and orbital 5. So remember, P has 3, D has 5. 1, 2, 3, 4, 5. And S only has the 1 because this is 1 orbital. F, well, it has 14 total electrons here. So it's going to have, what do you guys think? 1, 2, 3, 4, 5, 6, 7. Okay, because it's going to be 1 electron per orbital. Okay. Last couple of parts. Which of these is a D block element? So I want to know which one of these is located in here. So you have to compare those to your periodic table. I know that calcium is located in my zone right over here. So calcium is an S block element. So it's not a D block. Boron is located here. So it's a P block element, not D. Neptune, I believe that's what it's called. And P, let's see. Let's find NP. Okay. Oh, Neptune. Oh my goodness. Looking for MP. Oh, this is MB. So NP, ND, NP. Neptunium. All right, I was close. Neptunium. All right, so that's in the F block, still not the D block. And finally, gold. Gold is right here. That is my D block. So I'll just circle gold. And that's all you're doing is you're comparing it to where it's at on the periodic table. Which one of these has 7 valence electrons? 7 valence electrons. Okay, well, valence electrons are electrons that are located in the outermost shell, right? So that means it is possible for these elements to have up to 6 valence electrons. The only way you're going to have 7 is if you have an ion. So we're going to look for ions in this case. Bromine has 5 valence electrons. Oxygen on its own has what is that for? 6 valence electrons. And actually, no, I was wrong. Bromine has 7 valence electrons. Okay. I made a mistake. Sorry, I made a mistake. So it is possible to have 7 valence electrons. You don't have to be an ion. Please scratch everything I just said about that. The way you count your valence electrons is you're going to count them from here all the way over in your last energy level. My head, for some reason, started counting only the electrons here. So, all right, let's do that again. Okay, so to count the valence electrons for oxygen, you're going to have 1, 2, energy level 2, right? Right here. 1, 2, 3, 4, 5, 6. For fluorine, we have 1, 2, 3, 4, 5, 6, 7. So anything in column 17 is going to have 7 valence electrons. So bromine is in column 17, so it will have 7 valence. Oxygen will not. Oxygen with the -2 is going to have 1, 2, 8 valence electrons, so that ion won't do. And neon right here also has 8 valence electrons, so that one won't do either. So the only answer we have is bromine. Anything in column 17 or 7A. Right, so to give you that hint on that one, this is column 18 and it's going to have 8 valence electrons. This is column 17, it's going to have 7 valence. Column 16 is going to have 6 valence electrons. This one is going to have 5, 4, and 3 valence electrons. This one has 1 valence electron, and this row here has 2 valence electrons. Okay. So it all depends which column it is, and that's going to kind of guide you with how many valence electrons it might have. That's considering it's not an ion and it's not one of those going through a major exception to the rules. We usually don't get into those ones here, not until you get into Gen Chem with the rule exceptions, making things more, creating bonds with more than just your octet. Okay. Okay, so this one wants to know which one of them has the same electron configuration as neon. So it's asking for something that is isoelectronic. Okay, isoelectronic. So remember, neon, based on our periodic table, ends at 2p6. So you're going to have to find which one of these is at 2p6. Let's take a look. Okay. So my 2p6 is here. Given to me is sodium. Sodium is right here, so that's a no-go. Then we have fluorine, no-go. Lithium with the +1. Here's lithium, take away 1. That has the same configuration as helium. That's a no. Sodium with the +1. Sodium, take away 1. Brings me up to neon. So it's going to be sodium. All right. Now it's asking just basic little questions on how to fill things up. How many valence electrons do neutral alkaline earth metals have? So you have to figure out, well, which one of these is your alkaline earth metal, right? So let's see. This one doesn't show it, but you could easily Google alkaline earth, and it's going to be one of these two. That's going to be your alkaline earth metal, right? And you're going to say, oh, this one, or it must be that one, okay? But it's one of those two columns. By the way, if you pay attention, you could see that alkaline earth metals are in column 2. But all right, so look at which one's in column 2, and you're going to get your alkaline earth metal. So column 2. All right, you guys, I'm going to stop there. There's a couple questions I feel like you guys can answer the rest on your own. I hope this helps, and you guys have a good day.